right, let's look at putting concepts together. Let's look at this first problem. So at temperatures near 800 Celsius, actually, first thing I'm going to do is, you know that we never will use Celsius in our conversions. So let's just change Celsius to Kelvin right now. Let's do 800 plus 273 to get 1073 Kelvin. Okay, that's out of the way. So at temperatures near 1073 Kelvin, steam passes over hot coke, which is a form of carbon obtained from coal. It reacts to form carbon monoxide and molecular hydrogen. And here is our equation. Mixture of gases that results is an important industrial fuel called water gas. At 1073 Kelvin, the equilibrium constant for this reaction is Kp 14.1. So this also tells me that we're looking at the pressure constant. All right, pressure also meaning we're looking at just our gases, not solids, not liquids. What are the equilibrium partial pressures for water, carbon monoxide, and hydrogen in the equilibrium mixture at this temperature if we start with solid carbon and 0.1 moles, okay, we're given moles, which is an N value, right, of water in a 1 liter vessel. This is a volume unit. Okay, so first of all, Kp. We know that Kp is our reactants over our products. So we're going to look at the partial pressure of CO times the partial pressure of hydrogen divided by the partial pressure of water. Okay, so we need to figure out what the partial pressure of water is. And in order to do that, we can use, let's do this, let's solve for pressure. Let's see if we know everything else. We know the volume of water. We know how many moles of water. We know R is a constant, and we know temperature. So let's do P times V, 1.00 liters, equals, my N is 0.100 moles. R, we're going to use the 0.0821 so we can have atmospheres. And temperature is 1073 Kelvin. All right. Let's solve for P, pressure of water. And I'm going to do 0.1 times 0.0821 times 1073, all divided by 1. I should get the pressure of H2O as 8.81 ATMs. Check my math. Did you get the same? All right, now we know the starting of pressure. We're going to rewrite our equation here. We've got solid carbon plus water, gaseous water, in equilibrium with carbon monoxide gas and H2 gas. So let's make our ice table. All right, so we know that initially we have 8.81 ATMs of water. We also know that since this is solid, we take it right out of the equation. We also know that these are our reactants. We don't have any products initially. All right, we also know that in this reaction, we're going to lose some amount of H2O. And because they're all a 1:1:1 ratio, that means that our products are going to gain that same ratio of quantity. Okay, so at equilibrium, we're going to have 8.81 minus X, and here we're going to just have X, and here we're going to just have X. So let's plug what we know with our equilibrium data into our Kp. So we know that Kp is 14.1. And Kp is equal to the partial pressure of our products over our reactants. So we're going to have X times X, right? And they're both to the 1 power, so just X times X over my reactant, 8.81 minus X. And again, that's just to the power of 1. So let's simplify this equation. So this is over 1, so we're going to multiply this. So 14.1 times 8.81 minus X is equal to X times X is X squared. All right, so let's distribute, and we'll do 14.1 times 8.81. We would get 124.221 minus, and then that's going to distribute, so minus 14.1x. And then let's get x squared over on the left side, so we'll minus x squared, and then that will be equal to 0. Okay, now we're going to plug this into our quadratic program in our calculator. So if you get to quad, where we would plug in, A is what's attached to our x squared, so a negative 1. B is a negative 14.1. And C is 124.221. So let's see what we get here. A, negative 1. B, negative 14.1. And C is 124.221. Okay, we get two numbers. We know that pressure can't be negative. So we know that X has got to be 6.14. All right, so we're going to say X, 6.14. We're not quite done. We need to plug this X into our equilibrium up here. All right, so our X is 6.14. So let's do 8.81 minus 6.14. And that would give us 8.81 minus 6.14. So water's equilibrium pressure would be 2.67 atm. And this is just X, 6.14 atm. And H2 would also be 6.14 atm. And that just solved. I'm going to go down here. What are the equilibrium partial pressures of water, carbon monoxide, and hydrogen? Water, carbon monoxide, and hydrogen. Okay, so let's look at the second part of the question. What is the minimum amount of carbon required to achieve equilibrium under these conditions? So even though carbon is not included in our pressure equation that we did, it still is important in the chemistry in this reaction. So we need to look at, all right, we know how much water is also one of the other reactants. And we know that at equilibrium, water's pressure is 2.67 atm. So the pressure of H2O at equilibrium, 2.67 atm. We also know more information about water. Like, we know that there is 1 liter of water. So if I were to look at this equation, we want to find the amount of carbon. We need to find the amount of water first, and then we can just do mole to mole ratio to get to carbon. So let's figure out moles of water at equilibrium. We know the pressure of water, 2.67 atmospheres. We know the volume of water, we were told it was 1 liter. We know R is 0.0821, and we know the temperature was 1073 Kelvin. Okay, so let's do this, and we're going to do 0.0821 times 1073. Then we're going to divide 88.0933 to get n by itself. We're going to do 2.67 divided by that answer. So 2.67 divided by that answer, 0.0303. We also know that, just do this, if this is how many moles of water I have, we can look at our stoichiometric ratio and say, well, there's 1 mole of water to 1 mole of carbon. So it's a 1-to-1 ratio. So this many moles of water is equal to that many moles of carbon. And then lastly, to figure out, we can go from moles of carbon to grams of carbon. So we're just going to do 0.0303 moles of carbon. 1 mole of carbon is equal to 12 grams of carbon. So 0.0303 times 12 should be 0.36. How many sig figs do we want? Do we want 3? Yes, 0.364 grams of carbon are needed at equilibrium. We continue the problem at the top of the next page. Here we go. What's the total pressure in the vessel at equilibrium? Well, this is a Dalton's law here, where we just look at the total pressure. The pressure for the whole system is equal to the pressure of all of the components in it. So the pressure of water plus the pressure of carbon monoxide plus the pressure of hydrogen. So let's look at this. Pressure total is equal to, we're going to add up our 2.672 atm plus 6.138 plus 6.138 to get a total pressure of, let's do the math, I got 14.948. And if we were to run that to 3 sig figs, I'd get 14.95. Oh wait, I said 3 sig figs. Right? How many? Let me just double check here. How many sig figs? 3, we want 3. So we're running this 1, 2, 3. 14.9 is what it would be right there. So 14.9 ATMs. All right, so let's look at the next part. All right, for the next, at 25 degrees Celsius, the value of Kp is 1.7 times 10 to the negative 21. So the Kp, 1.7 times 10 to the negative 21 at 25 degrees Celsius. Well, we know that when we started, we had a Kp of 14.1, and that was at 800 degrees Celsius. So what's happening here? We started at 800, and we're cooling significantly down. So the temperature is really going down from 800 to 25. This is our starting point. And what happens to our Kp value? Our Kp value went from 14 to, wow, 1.7 times 10 to the negative 21. So 0.20 zeros and then 1.7. So the Kp went really far down. So that means that we are heavily shifting left. As temperature goes down, we are shifting left, implying that we have an endothermic reaction happening. And again, that Kp value is going down. And when Kp value goes down, we're looking at, remember, Kp is products over reactants. So if we are getting a smaller Kp, the reactants number is getting larger, 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 showing us that we're shifting left, which is endothermic reaction. All right, now to produce the maximum amount of carbon monoxide and hydrogen gases at equilibrium, should the pressure be increased or decreased? All right, well, let's think back to our equation here. We've got carbon plus water giving us carbon monoxide and hydrogen. So if we look at our products, we have 2 moles of gas. And if we look at our reactants, that doesn't count, right? We have 1 mole of gas because that's solid, it drops out of the equation. So we can manipulate the pressure. So let's say we want to produce the maximum amount of carbon monoxide and hydrogen gases. So we want to force the reaction this way to produce the most amount of carbon monoxide and hydrogen gases. So in order to do that, so to force more molecules to the right, we need to have low pressure. By lowering the pressure, we're going to favor the product side of this reaction.